Topic Notes 2.4, Tides and Currents. Now that you've learned a lot about the geology of the planet, it's time to get into the flow of things by learning about water and how it moves around. This is a picture from Munyon Island, one of my favorite parts of the Lake Worth Lagoon. And when you go there during high tide, it's easy to go in and navigate the channels in a kayak. But during low tide, you're going to hit a lot of sandbars. It's just an idea of what it deals with in terms of tidal changes. And of course, there's also the Gulf Stream, which is offshore. So let's get into it. It's time for our main ideas, and there's 3 of them. First, tides are formed from the gravitational pull of the moon and the sun and are different across the globe due to a variety of physical factors. Second one, the surface currents are caused by the interaction of global wind patterns and the ocean's surface. And finally, deep ocean currents are caused by a variation in density and form the global conveyor belt that redistributes things like heat and nutrients. Also, remember to pay attention to those individual learning goals, and let's get going. So first up are tides. Tides are the periodic rise and fall of the surface of the ocean resulting from the gravitational pull of the moon and the sun. Now, I do have to put a little bit of a point on this because students often get confused. The moon is the major force here, and that isn't because the moon is bigger or somehow has stronger gravitational pull than the sun. It's because it is closest to the Earth. The sun has a massive gravitational force. In fact, that's why everything in the solar system is revolving around it. So it does obviously have an impact. However, because the moon is so close to us, it has the more influence in terms of tides. But as we'll find out along the way, the sun has a very important role to play in tides as well. So both are at play here. Another thing to note is that the moon isn't exactly revolving directly around the Earth. What's going on is that the Earth and the moon together have a common center of mass, and they are both revolving around that point. Now that point happens to be inside the Earth. It's just offset from center. And so that's why it appears like the moon is revolving around the Earth. Now you may also notice that there are 2 bulges, one on the side of the Earth next to the moon, and of course another bulge on the opposite side of the Earth. Now where the moon is located, it makes sense. The gravitational pull of the moon is causing that bulge. The other side actually has to do with the centrifugal forces involved in the rotation of the Earth and the moon system together. It's kind of like when you are in the gravitron at the fair and it's spinning around and it's throwing you against the wall. That's sort of what's happening to the water on the opposite side of the Earth. Now, as the moon rotates around the Earth, it causes tides to rotate as well along the Earth's surface. Now, there are 2 patterns we can talk about. There's 3, but we're going to talk about 2. The first is semi-diurnal, and that's locations that have 2 high and 2 low tides each day, about 12.5-hour intervals between them. Then we have diurnal, where locations have 1 high and 1 low tide each day. There's also what we call mixed, which has a little bit of a variation in tide levels depending on what the circumstances are. Now this map shows you where the semi-diurnal, diurnal, and mixed tides are found globally, just so you can kind of get a lay of the water, if you will. And we on Florida's East Coast experience the semi-diurnal. So that's where we have 2 high and 2 low tides each day. Now we're going to talk about why these different patterns occur as we move along. Now a tidal range is the difference in height between the high tide mark and the low tide mark over the course of a day. This is also called tidal amplitude, and this all varies globally and from day to day. Now the image to the top right shows you the tidal range in the Bay of Fundy, which is in Nova Scotia in Canada, and it's one of the largest tidal ranges in the world. It's about 52 feet at its height, which is really crazy, and you can see the people walking around during low tide and then kayaking in high tide. Now the picture on the bottom right is actually on the other side of the continent of North America in the British Columbia side. And I did a multi-day kayak trip there, and we had our kayaks, and you can see all the rock bed there. That's low tide. during the night when we were camping on shore, we really had to pull our kayaks way up into the forest because the tides would come in and out overnight and it would move everything around. So you do have to pay attention to the tides when you're working in the water. So why does the tidal range change so much? Here's a few things. First of all, the gravitational effects of the moon and the earth and the sun, there's a dynamic there that changes, and we're going to get into that in just a few minutes. There's also physical features such as the coastline where the tides are actually occurring. On the picture to the right, you're going to notice the Bay of Fundy setup in Nova Scotia. Now look how this narrow channel kind of extends inland there. And at first, it's the tide's about 20 feet difference. Then it gets to 23, 26, all the way up to 40 and 48 feet to 49 feet in the narrower channel. So all of that water is being funneled into the much more narrow area, and there's nowhere for the water to go but up. And so it kind of focuses that tidal push of water, and the height increases. Now, another thing can be environmental factors such as wind and air pressure and the size of the water body. So if you have a ton of wind pushing on shore, that may amplify your tide, and that might be just a daily issue. That might change due to the wind strength. And air pressure, of course, this has something to do with hurricanes, for example. Low pressure will actually increase the height of tides as well. Now, if the Earth had no continents and it was equal depth, we'd have a pretty predictable tidal situation in terms of everywhere would be pretty the same. The tide would just keep rolling around the Earth with the moon. But we don't. We have continents. And so this actually sets up a series of what we call amphidromic points, which is not something you're going to be tested on, but just to kind of know. And if you look at this graphic, you'll see these kind of pinwheel lines going around these points. Those are amphidromic points. The tides are essentially rotating around those points. Now, the reason why I bring this up is because there are variances in tides based on whether you're in the coastal regions, if you're in open ocean, or if you're in seas or lakes. Now, if you're in open oceans, which are mostly where those big amphidromic points are, you're mostly not going to notice a lot of change in terms of tides because they're going to be rolling under you in that deep water. Now, when you get closer to the coastal regions where it becomes more shallow, then the tides are going to be way more noticeable. However, if you're in a smaller body of water, like a smaller sea, like the Mediterranean, for example, you're going to have rather minimal tides because it's not going to have enough space to really make as big of an impact. And then, of course, if you're in smaller lakes, like Lake Superior, for example, is a big lake, but it's smaller than the ocean, there is a small, almost imperceptible, there's a small noticeable tide difference, but it's very, very minimal. Something like at Lake Okeechobee, you don't really see much of a tide in it at all, although technically it's there. You just really can't register it unless you're like measuring in micrometers or something. Now, we mentioned already the shape of the shoreline, and here's some interesting fun benefits of this. There's something called a tidal bore that occurs, especially when the tides are moving up a very narrow passage like a river mouth or something like that. And the tidal bores can end up being very surfable, as they may say. Here's a picture on the right of the Grande River in France, and that can provide surfers with up to a 20-minute steady ride in with the tide, which is kind of interesting to see. Now, of course, you have to remember that outside of that narrow channel on the open beach, the tidal range is going to be much shorter as the water volume is spread out over a larger area. Next up, we have what we call a tidal surge, which is the coastal flooding of an abnormally high seawater level associated with a low pressure system, usually things like storms, hurricanes, stuff like that. Now, this can be a couple of things. First of all, the high winds can push water on shore, and also low air pressure can also allow the tide to come up a little higher than normal. And this, again, occurs during these tropical storms. The picture on the right is actually of Hurricane Matthew in Florida in 2016, which had a particularly high tidal surge going on as well. And of course, the higher the category of storm, the more of this you'll see. Now, if you remember a little while ago, I mentioned how the sun, earth, and the moon and their positions can affect tidal range. And so this is where we're going to talk about that. So there's something called spring and neap tides. Now, one thing to remember is that this has nothing to do with seasons. I wish they wouldn't have called it spring tides, but people get all confused about that. Essentially, a spring tide occurs when the sun, moon are aligned, causing the largest tidal range. This occurs during the new moon and the full moon, so it actually occurs twice a month, all year long, twice a month, all year long. Again, it's not about just being in the spring. And if you look at the diagram here, you'll see that the full moon and the new moon, whichever one we're looking at, and the earth and the sun are all in one straight line. This amplifies the gravitational effect of the moon and the sun. Essentially, they're both pulling in the same direction. So your high tides are going to be higher and your low tides are going to be lower. Now, neap tides are the flip of that coin, right? They occur when the moon and the sun are at right angles from each other, causing the smallest tidal range. This occurs during the quarter moon phases. So again, if you look at that diagram, third quarter and first quarter, at that point, you could draw a line through the earth and there'd be a 90-degree angle going to the sun from the moon, earth, and sun. So you've got that change. Now, this is where the sun and the moon are pulling the ocean in opposite directions, or at least in different directions. And in that case, the high tides are not going to be quite as high, and the low tides are not going to be quite as low. So you're going to have a smaller tidal range. And again, it's because they're both pulling in different directions. All right, it's time to start talking currents. A current is a continuous physical movement of water caused by wind or density. And to the right, you actually see an old map showing the Gulf Stream coming up from Florida and, of course, what we call the North Atlantic Drift eventually at the top there in the north. Now, currents carry with them nutrients, dissolved gases, heat, living organisms, and even sediment. And that's why currents are really a big deal in the ocean. Now let's start with surface currents. Surface currents are typically driven by global wind patterns. They are steady and they're dependable. This map shows you all of the major surface currents around the world. There are definitely some minor ones. You'll probably recognize a few, like the Gulf Stream that goes up the west side of the Atlantic Ocean. Then you have the North Atlantic Drift. And then on the east side of the Atlantic, you have the Canary Current bringing it back down, and the North Equatorial Current that brings it back to the Gulf Stream, which creates a gyre, which we'll talk about too. But first, we need to talk about global wind patterns because this is, of course, a major consequence of why we have surface currents, right? Now, the Earth experiences uneven heating from the sun, essentially meaning at the lower latitudes towards the equator, you're going to have the highest concentration of sunlight, and it's going to warm things up the most. That's why it's warmer at the equator. At higher latitudes, that sunlight is going to be dispersed over a larger surface area, and you're going to get less heating from it. So why do we care about this? Because that unequal heating sets up the traditional global wind patterns that you may have heard of before, like the trade winds, the westerlies, things like that. Essentially, it forms atmospheric convection currents. Some areas, like the equatorial regions, have excess heat, causing air to rise because it's low density, right? And as it rises, it cools, becoming more dense, and then sinks, generally in areas with less solar radiation. For example, there's sinking at about 30 degrees north and 30 degrees south. And so that is an area of sinking air. In between, you have wind, which goes from that dense high pressure at 30 degrees to low pressure at the equator at 0 degrees latitude. Now, wind does not just go straight from 30 degrees to 0 in a straight line, and it can't do that because the Earth spins. We have something called the Coriolis Effect. And a Coriolis effect, as a result of the Earth's rotation, the movement of wind curves clockwise or to the right in the northern hemisphere and counterclockwise or to the left in the southern hemisphere. So the big takeaways here are as follows. The Earth is unevenly heated. meaning you have buildup of low pressure and high pressure areas due to that unequal heating. Now, wind forms as air moves from high pressure to low pressure. Now, as that happens across the Earth's surface, there's something called the Coriolis Effect. As the Earth rotates, it's going to essentially curve that wind flow in one direction or another, depending on what hemisphere you're in. The results are the global wind patterns you see today. In fact, we call the trade winds because it would actually bring Europeans over to the New World, right, to North America. And the westerlies would bring them back to Europe. So we've used these for much longer than you might think. Now, as wind blows across the surface of the ocean, it creates currents. Essentially, it's pushing the water in that direction. Now, the water, as it's being moved in that particular direction, is also impacted by the Coriolis effect. Essentially, surface currents are deflected at about a 45-degree angle to the direction of the wind because water is more viscous and it moves slower. So it has more of an amplified Coriolis effect as it's moving in one direction or another. Now, the results of this is that surface currents combine into these gyres that I talked about before, these circular patterns that span ocean basins. Now, this happens because as the wind is pushing the water and the Coriolis effect is deflecting that at a 45-degree angle from the direction of the wind, you end up piling up water on the western side of the Atlantic Ocean, for example, and it can't go through the continents. So that's why it gets piled up there. And then the Gulf Stream essentially curves it to the north, where it gets picked up again by the winds, the westerlies, and pushed towards Europe. But again, it gets deflected 45 degrees again, and it starts to come back down into the Canary Currents because it can't go through Europe, it can't go through Africa, right? And so then it gets picked up again and pushed east again, and that's where you have the equatorial currents. And so you just get this circular motion because of the direction of the wind, the impact of Coriolis effect, and the fact that the continents are there and water can't move through the continents. All of these factors come together to create these gyres, and each of the ocean basins have a gyre. So now we can get into deep water currents. Deep water currents are driven by variations in water density. Now, this takes a couple of definitions. There's something called thermohaline circulation, which Greek thermos equals heat and hails is salt. So it's a large scale ocean circulation caused by density differences due to temperature and salinity changes in the world's oceans. Now, this results in what we call the global ocean conveyor belt, which is a constantly moving system of deep ocean currents driven by thermohaline circulation. So we're going to follow the formation of this deep water and its pathway throughout the world's oceans. Now, it starts as water freezes into sea ice. It leaves the salt behind. So the salt doesn't freeze. This cold, high salinity water will downwell or sink. Now, this happens generally in the North Atlantic, just around Greenland. And then it goes underneath the Atlantic Ocean and it snakes its way all the way to Antarctica, where another downwelling occurs and additional high density water is added to the system. Now, from the Antarctic, the deep water flow splits into two directions, one towards the Indian Ocean and the other into the Pacific Ocean. Now, once in the Indian Ocean, the water will actually head towards the equator. As it warms, that water comes to the surface along the eastern African coastline. That water then continues as surface currents, looping back around. Now, the Pacific deep water continues north past the equator. As it warms, it rises to the surface along the western coast of North America. That water then continues again as surface currents towards Australia and into the Indian Ocean. Warm surface currents bring water back into the Atlantic and then north towards the pole once again, where it again will go through that formation of deep water just around Greenland. The global conveyor belt is very important. It can bring cooler, drier weather to coastlines that would normally not see it due to their latitude. And also it can bring warm, wet conditions to coastlines that would normally be cooler. Now, if you look at the graphic on the right, you'll notice a series of temperature lines in Celsius, 25 degrees, 20, 15, 10, and so on. Now look at those, we'll look at that 25-degree line. Look at where it crosses North America. It's just around the top part of Florida. But look at where that 25-degree line is on the coast of Africa. It's much lower in latitude. This is because that cooler water is being pulled down on the western side of the Atlantic Ocean, whereas the warmer water is being pushed up on the eastern side through the Gulf Stream, whatnot. So this whole process of moving things around like that is very important, because if you look where Europe is, if you go across to the same latitude in Canada, it's a much cooler system. It's a much cooler environment. Whereas, Europe actually has a little bit more rain, a little bit more warmth than it would normally have without that current. You'll also probably notice that the surface currents and the deep water currents are connected in one big system. So just keep that in mind as well. That was a lot of ocean in motion. So here's again those main ideas. Tides are formed from the gravitational pull of the moon and the sun and are different across the globe due to a variety of physical factors. Surface currents are caused by the interaction of global wind patterns and the ocean surface. And deep water currents are caused by variations in density and form a global conveyor belt that redistributes things like heat and nutrients. All right, everybody, until next time, keep learning.